Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/Linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host, as usual, is Tobias Macy, and today I'm interviewing Scott Lundberg about SHAP, a library that implements a game-theoretic approach to explain the output of any machine learning model. So, Scott, can you start by introducing yourself?
My name's Scott. I work at Microsoft Research right now, and my primary area of investigation is, model transparency, model debugging, and explainability in general in the AI ML space.
And do you remember how you first got introduced to Python?
I don't actually know how I first got involved with Python, but when I first started using it, in a meaningful way was a research company where a lot of stuff was either done in MATLAB, but Python was the open alternative. And so I was pretty drawn to that. I feel like libraries have matured over the years, but, when compared to MATLAB, it was a clear sort of easy to take my code wherever I needed to and take the expertise wherever I needed to. So,
yeah, it's definitely a very common theme that I've come across, especially for people who are working in research or academia, saying MATLAB is great until I don't have a university paying for the license.
Yes, exactly. Or a company in this case. So, but yeah, that's how I got engaged in, Python, Jupyter, that kind of ecosystem kind of caught me and I stayed.
And so now you're working on the SHAP library, as I mentioned at the open, and I'm wondering if you can just describe a bit about what it is and some of the story behind how it came to be and why it is that you are focusing your time and energy on this specific area of effort and sort of why you decided that it was useful to have this as an open source library for people to be able to use.
And the purpose, as you say, is to explain the predictions of machine learning models based on game theory. But how did it come to be? Well, actually, I was doing my PhD in comp bio, so ML applied to, biology and medicine and things like this. And one project in particular that we were working on when SHAP got developed was an adverse event prediction during procedures in hospitals. And, there's a lot of interesting data that's collected during those types of procedures. You can imagine, it's one of the most measured points of your life if you're going in for, a surgery or something. But if you just turn on a red flag that says, I think this bad thing might happen, as a doctor, what are you supposed to do, right? We're sitting in the room talking to doctors, and they're like, okay, the red light turns on, you mentioned, hypothetically, in the system. You just look around, you're like, something going to fall out of the air, is the patient, you just have to check everything, right? Because there's no understanding other than the outcome. That was the need, I guess, that drove initial interest in, developing something concrete for transparency. And so as I got into the transparency side of things, I dug into a lot of the work that was going on, and actually a collaborator and friend of mine, Marco Barrow, worked on Lime, which wasn't actually written at that point, but he was working on it. And so I was trying to use some of the stuff that he originally developed in sort of these local models. And then when I connected that in with, we tried to train some linear models, so some inherently interpretable approaches. And then I got really interested when I connected all those things back to some approaches that had been introduced before on Shapley values for explainability, but hadn't been widely applied in my experience. So yeah, I got into that, got really interested, found a lot of interesting connections, and at least what I found engaging. And then I actually wrote it all up in Julia in time, just for speed purposes. But then some other grad students convinced me that it would be probably useful as an open source library. It's hey, I want to use that too. You should probably really push this out. And I think it was a good advice.
In terms of the sort of nature of explainability, and as you mentioned, when you have the output of a machine learning model, in some contexts it can be useful and sufficient to just say, this is the answer. But for the case that you were giving, in the medical context of this is the output, but now what do I do with it? And why is it saying this? The real value comes in understanding the reasons that a given model gave that particular output. And I'm wondering, what are some of the sort of contexts that create that need to be able to understand the reasoning behind the outputs? And what are some of the evolutions in the sort of architectures and approaches to machine learning that have made explainability such a challenging problem?
Obviously, we just described one, which was the motivating factor. And that was actually, maybe less typical for most use cases today, because I would say model debugging is actually the easiest off-the-shelf use of explainability tools today, particularly by data scientists, people familiar with coding. As soon as you build a model, almost your first question is, what did I build, right? Not just like, I know the name of it, I know like the form that the parameters may take, but I'm curious, like, what is the actual statistical signal that I pulled out of my data? It's really what interpretability is trying to get at, both at the local level of like, what is the signal that is driving an individual prediction, and what is the signal, what's the information content that's really driving, the model as a whole, either by representing some global pattern of like this feature as it, changes its value, how does that affect model output, kind of partial dependence kind of views, or global measurements. Yeah, so all of those are kind of like an intuitive need that I think most people feel when they built the model. I at least feel it. I got down this road. But then there's also like specific, outputs that are almost quantitative, right? So you could say, I want to know how much my model depends on features that I believe may be spurious correlations. One potential, just so that I can understand how my generalization may or may not suffer when that happens. If you have a medical model, for example, like being able to understand the structure and the behavior of that, I think is quite important, because often your downstream action will depend on the reason the prediction was made. That was the case that we ran into with the doctors, for example. So one thing that we found was lots of spurious correlations in a hospital setting. So let's say, for example, that I'm a doctor and I give you treatment for something that's supposed to make your risk less. Now, the only reason I would have given you that treatment is because I, as a doctor, am concerned. Right? That actually you need this, right? Otherwise, I wouldn't be giving you this drug. So as soon as the model sees that you got dosed with this drug, what does it learn? It learns that you got dosed with the drug, but also learns doctor concern. Turns out doctor concern is actually a much more significant signal than the drug's risk-reducing effect. And so overall, it turns out to be, the model is actually increasing your risk. So if you ask the model, like, what's the best way to make this person look healthy? They would say, well, don't treat them and don't do anything that you would do if they were sick. That's the kind of stuff that you learn by looking inside a model that you just wouldn't if you weren't. Maybe outside a medical setting, if you were in like a sales type call, like someone called and you're tasked to call up someone because they're likely to, cancel their service. Well, if you were told that they're likely to cancel their service because they're a kid, it just turned 18, and for some reason the model thinks that's really likely for them to cancel service at that point, like that's a lot of context. It's valuable when you walk into a conversation, so you're not coming in blind. Or if like the model's recommending pricing for a particular customer for a variable pricing scheme, like why that pricing is recommended really helps you have some, context for the negotiations as you get started. Or if your approval, like if you're there trying to approve applications for whatever, insurance, loans, imagine whatever, oftentimes there's a threshold where like, really small ones, you just let the computer do it, but like higher risk things, people are involved, that borderline, that's another case where these types of systems get involved at the model consumer stage and not just at the model debugger stage.
And then another sort of interesting element of the problem of explainability is the rise of deep learning as the sort of first stab that most people will take at trying to create some interpretation of their data, where they want to be able to just say, throw a neural network at it and it will come out with some output, and then I'll determine, what is the level of accuracy, how do I want to tune it from there, without necessarily understanding what the sort of statistical significance of their inputs are to the output. That's where sort of a lot of the lack of understanding comes into sort of machine learning as a discipline. Whereas if you were building the model based on all of these sort of statistical theoretical approaches of, I have these inputs, I want to be able to, do k-nearest neighbor clustering because I want to understand what are the sort of populations of data that I'm dealing with, then you have a better understanding of like why a model gave a particular output because you used this clustering approach. Whereas if it's just throw it into a deep neural network and hope that the, different layers are attaching to the appropriate signals and not just, the background color that happened to be present in all of these sort of correlated pictures. And so I'm wondering sort of what you have seen as the impact of, the evolution of machine learning approaches and architectures in the sort of utility and challenge of being able to create these explanations of how these outputs are generated.
Well, certainly deep learning is prone to create opaque systems. I think everyone would agree with that. Not that you couldn't create things that are not opaque if you're careful enough, right? They're just linear models stacked up in many cases. But I would say that, well, first of all, they probably ignited a significant amount of interest in transparency at an agnostic level. And I think that may actually have a side effect of being beneficial for traditional statistical models that you might consider otherwise interpretable, because often it's easy to conflate interpretability with implementation, if that makes sense. If I have a k nearest neighbors model, I may, and rightly, say that there are ways to interpret that. I understand exactly what happened. But it turns out that there are many questions that might be difficult to answer with a k nearest neighbors model, which might actually be the real question that you have for whatever downstream task. So let's say, for example, you're supposed to rank your features by most informative. Not saying it's impossible with a k nearest neighbors model, but it doesn't come out right away. You don't just look at it and be like, oh, well, this is the most important feature that's really driving what's happening. And same for a decision tree. Like I could write a small little decision tree and I could say, oh, I know exactly what's happening because I can execute it in my mind. But it doesn't mean I know what's the most important feature. Like I have no idea what the most important feature is. Hopefully it's the top one because that's how it splits, but there's no guarantee. And so I think there's actually a side benefit that neural networks have positive and agnostic view. And this decoupling of what does it mean to have a good explanation, I think should first be posited separate from what you have as a model. That's your goal, right? And your goal, it lives separately from your implementation to get there. But that being said, going back to the different structures of the neural nets themselves, I would say that as they get larger and larger and larger, well, there's really two challenges. One, I would say that in the nitty gritty, there's explanation methods that work by backpropagating stuff through the network, right? Those I have found get harder and harder as networks get bigger and bigger. And they do just because the dependence of the outputs on the inputs is just more and more abstract. So if you take ResNets are a good example of really deep networks. If you were to try and use things implemented in SHAP, even like the deep explainer or the gradient explainer, from the pixel level all the way to the output of a ResNet 50, you just look at the results, they're not good, right? It's just scrambled by the time they're through 50 layers. If you go into maybe from the last layer to something closer to the head, well, then you're going to get more reasonable, maybe at least go 10 layers in and now you're okay. So I think that's one thing is the farther and farther away you get from the inputs, the more sort of implementation specific methods begin to have trouble because they're approximations, and those approximations get worse as they get stacked more and more. You could say, okay, that's fine because agnostic methods, which simply rely on executing the whole thing, don't care about the input to output distance, so to speak. They just care about the complexity. In there, I would say that some of the biggest challenges for these neural net models is the fact that they are best, right? Neural net models are best for distributed feature representations. So things like text, pictures, sound waves, all these things where deep learning is state of the art and there's not really any competition for it even, are areas where individual features are not independent from each other. They should not be interpreted very independent from each other. And it's very much about extracting what we would consider sort of a separable signal, but from a large area of the input. And that, I think, causes a lot of challenge for interpretability methods because if you use as a language pixels or as a language, slices of a waveform, there's only so much you can get from sort of the heat map view of the world. And so I think the actual, creation of features that are a good language to use for explanations becomes almost an equivalent challenge to the sort of summarization task, right? Because SHAP does a lot of summarization, here's how you can summarize the interaction effects. But if you don't have good starting terms, then you're limited.
And are there particular sort of applications of machine learning and sort of data formats that you're dealing with that increase the sort of complexity? You mentioned things like working in the level of pixels or in the level of, segments of a waveform, but are there any differences in terms of, deep learning approaches to natural language processing where you might be using a transformer model or, doing transfer learning using some, large multi-billion parameter model that you then want to just strip out and replace the last few layers of, or, some of the different sort of neural network architectures where, a CNN versus an RNN, if there are any of those factors that will influence some of the complexities of being able to actually understand what was the reasoning that went through this.
Yeah, well, so if you're using a CNN, pretty much everyone who's them for much has almost always looked at last layers, right? The last conv layer before you go into a flat feed forward or whatever you have up in your head. And, that has still some spatial encoding in it. And that I think is unique, obviously, to the structure of the data and is something that will always make explanations better, right? So whenever you're thinking of explaining, networks like that, you always have to think, what is this spatial proximity? And if I want to look at the internals of the network, then I can always do better by looking at it. But if you think about it, what we're really leveraging there is the fact that we sort of downsampled, right? And we've also shortened the model. So maybe we could do like gradient propagation, like GradCam is gradients come back. Like that works pretty well once you've got close enough to the output. What other thing that we've tried in SHAP is to try and leverage the structure of the input data to minimize the number of perturbations that happen, because the complexity of doing an agnostic explanation is the fact that you can only execute a model so many times before it becomes computationally intractable. Right? So you could say, oh, it's really easy to understand the importance of every pixel. Just toggle it on and off in the context of all other pixels being on and off. What is this? 2 to the 256 times 256? Like it's, more than the number of molecules in the universe. So like you can't do brute force type approaches, but you can leverage the structure of the image. And even simple things like we built like our current image one in there, I think is like a recursive partitioning tree, right? So it literally cuts the image in half, toggles both halves, whichever half mattered more, it recurses on that and sort of does an A-star search. So like that is very dependent on the input structure, right? The fact that it's, structured like that. I think the same thing for transformer models, except transformer models are even, in my experience, can be, even bigger depending on which language model you're talking about. So what that means is the number of evaluations, again, has to be even more sensitive. So obviously you have attention maps, attention masks that can give you some feel for like what heads are doing. But my experience is that you're always better off just actually perturbing the input and seeing what it does. And with the right heuristics, you get better at that point. So maybe the big takeaway there is as you get bigger and bigger models, it's easy to look inside them and find pieces that you think behave. I find myself more and more leaning towards just changing the input and seeing the behavior because I've anchored myself across the whole system and I don't have to make as many assumptions.
Digging deeper into sort of the concept of explainability, we've talked about sort of being able to understand the context and the reasoning behind a given output. We've talked about being able to gain some sort of heuristics and try to have an intuitive understanding of where the model is, taking a certain direction based on the given set of inputs. But more broadly in the concept of explainability, are there sort of different ways that that term is used sort of in industry and particularly in the context of like regulatory systems such as GDPR or CCPA, where you need to be able to say, with some level of confidence or definition that this output was given from this machine learning model, and now the consumer needs to understand what was the motivation for that decision, for like in the context of an insurance claim, for instance. And sort of what are some of the degrees of specificity and accuracy that are necessary for being able to establish these explainability thresholds?
Isn't that a question worth a lot of thought? Right?
Yeah, there's somebody's thesis right there.
Yeah. I think that one piece that's important to remember about explainability, particularly for technical folks, is that there are people involved. And unashamedly really like the sort of theoretical side of things and like axioms that show uniqueness and stuff like this, but they're assumptions. And whenever you have explainability to a person, right now, I personally think explainability could be consumed by a downstream machine as well, right? There's no reason that like the signals that are produced by these explanation methods are not also valuable for downstream processing. We can talk about that later. But when you're communicating to a person, what really matters is the mental model that the person arrives at the end of the day, and how that mental model impacts, how their mental model of the world shifts because of your explanation, and then how that affects their behavior. So maybe, I won't try and define for governments what they mean by the laws that they put out, but I do think that there are a couple of things to keep in mind. One, when you say specificity, like how much specificity is important, I think what you mean is how many details can we leave out versus how much do we need to communicate when we're writing explanations. And I think that explanations come in various forms. So first of all, like when we wrote up SHAP, like we basically said like an explanation is a model, right, formally. And so it's a simple model that represents the more complex model in some way. that is meaningful. So for SHAP, that's just an additive model. So a set of feature attributions that add up to what it would have been for one person versus what it would have been for another. And maybe it's good to be concrete here. So like if I have two people who both applied for an auto loan, like you said, one's named Bob, one's named Sue. Bob gets a score of like 520. Sue gets a score of 600. Sue gets the loan, Bob doesn't, right? Explaining to Sue and Bob like what happened. Like if there was no one but Sue ever in the history of the universe, then explaining what happened is sort of doesn't really make any sense, right? Like there's always has to alternative, right? Whenever you say like this happened, it's always because this happened instead of something else. So for Shapley values, that's like the background distribution or the alternative. It's some way of masking the features. So if I was explaining Sue and Bob, let's say they filled out a 10-point form, I could literally take the input form values from Bob and one at a time replace them with Sue's values and observe as I did each one how the score changed. And eventually I would get to Sue's score because I filled out the whole thing. So if I have a very simple model like a point system, right? Like if the true approval process was just a point system, +1, -1, +2, 0.2, then I would just read off those points when I did that. And so then I would give that as my explanation. And people would call that maybe an inherently interpretable model, and a model with, that just I can read the whole thing off. I don't need an explanation. Or maybe a better way to say it is that the model is its own explanation. Or maybe it's not even a point system. Maybe it's a linear model, right? Well, if it's a linear model, I can still just do that thing, and I'll read off sort of the difference between the, beta times my xi for Sue and my xi for Bob. And that'll be my explanation of each feature, and that makes sense. But once I get into nonlinear models, then the order that I fill out the form actually matters, right? Because, if two things are sort of in an and relationship, then whenever the second one gets put in, that's when I see the bumps, which changes the order. And that's fundamentally where Shapley values come in and say, how do we distribute the credit for these, what we'll call interaction effects, right? These non-additive effects between the input features on the output. So when you say, how much specificity do we need? My mind immediately goes down to, well, how much are we hiding from the user mathematically? Because that's different than the psychological question, but at least on the mathematical side, we can say, how much are we hiding from the user? And I would call that, like, I've been using the word explanation error, right? So like, what is the error in the explanation? In other words, how much does my explanation model deviate from the real model over the set of perturbations that I'm considering, which in our case are just toggling between either a background state or the current state. So I would say that whenever you're providing an explanation, you need to consider the explanation error, right? And if you apply, for example, this sort of additive point-based explanation to a linear model or a generalized additive model or a point-based additive model, like if you were to apply SHAP to any of those, you would end up with zero explanation error, right? In the sense that there's no deviation, so everything would be great. As soon as you start adding more and more interactions, like some deep multi-layer neural net, you're going to get non-trivial explanation error potentially. And then, you can get the standard deviation of the discrepancy, and you want to look at that and be like, okay, well, if I'm hiding 10% of the variability of what's going on, how much is that hiding from the user? And those are the trade-offs I think people should keep in mind when you're in this sort of high stakes, if you will, decision-making system. So that's all on the side of like math. How much do we hide? How specific do you need to be? But I'd be amiss if I didn't mention another question, which is, what is the purpose of explanation? So we actually had the opportunity to be a part of like a hackathon for the CFPB, which is a regulator here in the US on consumer financial protection. And they had a hackathon on action codes, and a bunch of people participated. And so it was a fun time to sit down for a week with experts who are in this field and ask the question, how do we explain, right now, this is how we explain rejections for like a mortgage application. How could we potentially improve that, or what's different? And one key thing that I think that there are actually multiple reasons that people want explanations. One is they want sort of the ability to see if there's like, bad data on their credit, right? Like if you rejected my application because of something that's wrong, like it's a typo, or like you've got some identity theft or something like that, like that's a clear thing that you would want to know. You might also want to put a little extra pressure for fairness and accountability on providers, so that if they say, no, the most important reason I declined you was your music taste, then people will be like, that would rightly make people uncomfortable. Now, that's more of like an informational thing, right? Like, what is the most important feature? What was the feature that if I didn't know it would have changed the prediction a lot? So you could think of measuring that in bits almost. But there's another very valid reason, and that is I might want to fix my score, right? Like I might actually want to have a better score. And that is a very different question, right? That's a question of what is the most actionable. So turns out that the current status of things is they provide something called a reason code, which leave a lot to be desired, but are essentially the first. And SHAP is also very much the first. It's like, what's the most informative? But you could also say, like, what is the most impactful counterfactual I could do? What is the thing I could change that would be the easiest to change and have the most effect on my score? And at a very rough analogy, it's kind of like the difference between how far am I from the mean on a partial dependence plot, right? So like make a partial dependence plot of your model, take the mean of your data, pick that part of the partial dependence plot, and then pick the person you're interested in, me, and see at this point on the y-axis of my partial dependence plot, if I had moved to the mean, how far would have I gone down, right? That's how far I am from typical for this feature. And that's actually the SHAP value of a GAN model. And also basically what's currently in reg from what I understand here in the US. But if you ask, what's the most effective thing I could do? Well, that's different. That's more like the gradient. Like, I don't care how far from the mean I am. I want to know the slope. Like, presumably that the x-axis is easy to change, in a uniform way. Like, the slope tells me how much bang for a buck do I get if I don't open more credit cards or if I don't do something else. So I guess that's a two-pronged question. One side is consider explanation error. When you're doing it, you're producing your explanations. And the other side is ask the right question. And oftentimes you may need different explanations for different outcomes. Like, I think people should have action codes just like they have region codes because it makes sense. But that's for others to decide.
Well, that's definitely a very fascinating answer to that question. So I appreciate the level of depth and rigor you gave there. And so now digging more into SHAP specifically, I'm wondering if you can talk through some of the sort of implementation details of how you're building it, some of the sort of workflows that you are designing around it, and sort of the ways that it is sort of architecturally structured to be able to integrate with all of these different sort of various machine learning workflows and frameworks and model types.
Learned a lot through the last 4 years, I suppose, that it's been a while with people interacting with it. So maybe a good way to start with just how things are structured in sort of a class hierarchy, if you will, right? So inside SHAP, there are things called models, right? And that's what you give to SHAP, right? You're going to give SHAP a model, and presumably you're going to at some point give it some data that you want that model to run on and get explanations for. So what it is that takes a model and the data and then produces explanations is what we call an explainer. An explainer is, the algorithm for summarizing these interaction effects. The tricky part for Shapley values, they're very easy to write down, but they happen to be NP hard to compute. And so that makes for all the interesting parts. And you can address NP or hard problems, I'm not sure if it's complete, in two ways, I would say. One, statistical approximation, right? Random sampling, just take a convergent estimate. Or two, restrict your domain. Right? So it may be NP hard to do it in general, but it might not be NP hard in a certain class. So SHAP has examples of both in the package. There are various explainers that are tailored for different scenarios. So maybe one of the most popular ones is the tree explainer, and that one is targeted at ensembles of trees. So this is random forests, gradient boosted trees. Trees are a superset of additive things. So that would be any generalized additive model, anything like that. And that is a nice scenario because there we can solve it analytically in low order polynomial time. So that's got like its own C code, and we can go into the details of the implementation later, but that's like a nice little bundle, and you would definitely want to use that for any tree-based model. And in fact, that code lives inside like GBM and XGBoost as well, inside their packages to deliver explanations, even if you don't have SHAP installed. But if you don't have that type of model, it doesn't help you at all, right? So there's other methods that are entirely agnostic. So one is like a permutation explainer, where it just literally walks through, like we talked about the form, fills them out one at a time, and that will apply to anything. But it doesn't account for the things that we talked about for images or text, right? So, in images is a lot of structure and spatial things. So we have other explainers that are targeted specifically on very structured inputs like text or images. And those actually come with direct integration with, the text ones at least come with direct integration with Hugging Face. So you can just pass a Hugging Face pipeline directly to the explainer, and it just automatically produces all this stuff. So there's this whole list of explainers inside there. And what we found is that users often, and rightly, would be like, oh, well, which explainer am I going to use, right? Like sometimes it's obvious because I have a XGBoost model and here's trees and, I understand what I want to do. But sometimes I have this particular deep learning model. Which of the options should I use? So what we ended up writing was just a SHAP.explainer, which is a class that will essentially like automatically subclass to whatever explainer is most appropriate. So you just pass it whatever, and it'll do its best to guess. So yeah, that's kind of like the hierarchy of explainers. I would say that an important piece of this, though, is that there's also something called a masker, right? And this really determines how do we actually perturb the inputs. So maybe a visual way to do this is to talk about images, right? Like how would I mask out an image, right? Like I could replace it with black. Is that what I mean when I like, how important is this half of the image? Well, what does that mean? Is like versus it being black versus it being like imputed by a GAN, like versus it being infilled, et cetera. And so different people will have different answers to those questions. Do I want to integrate over a whole distribution of possible things that it could have been? Same for tabular data. For most tabular data, you want to integrate over a distribution. And so that's the masker. The masker determines how are we masking things. And we have a whole set of those for masking text, replacing with mask tokens, deleting the text, like, setting the attention layer to 0. These are all different ways that you might want to mask things, and they're important choices. So we try and expose that as maskers and let people use a set of them or write their own, right? And then we also have some utilities to help people merge models together, right? So if I have a model that takes 2 inputs and then somehow they get merged and then they get added to another thing, and you can essentially create composites of these maskers until eventually you have like something that can handle a list of tensors that is whatever goes into your model with the appropriate way of masking it.
And so for people who are using SHAP and they are trying to build a sort of deep neural network that is, doing transfer learning on a BERT model to be able to understand the sentiment of a piece of text, what would actually be the process of saying, I'm now going to take SHAP, I'm going to integrate this into my workflow, and then I'm going to try to understand what are the most important features for determining the sentiment given this piece of text that I have contributed to this model?
So let's say you have your model in a notebook, working in a Jupyter notebook, and you're using Hugging Face. You download your pre-trained sentiment analysis from wherever. You have your data set. So now you have your model, and you're going to have a tokenizer, right? Because you need to be able to tokenize your input text before you throw it into the model. You can pass the Hugging Face model directly to SHAP.explainer as the first argument to the constructor, and the second argument would be the tokenizer. And the tokenizer becomes the masker. Okay, so SHAP detects that you've passed a tokenizer from Hugging Face, and it says, oh, I know how to turn that into a masker. And so it wraps it up. And then it sees that you passed it a model from Hugging Face, and it says, well, this isn't just a standard Python function. This is a Hugging Face model, and I know about those, so I'll automatically wrap that as a model that I know how to deal with. And then what comes out of that, what you constructed, is an explainer, which is a callable object, which takes as arguments the same arguments that your model takes. So in this case, be a list of strings. So you pass a list of 10 strings, and then you would get back out an explanation object, which is essentially an array of SHAP values for each sample. Now it's a bit trickier for text because, of course, the dimensions don't line up the same way that they would if you had passed a pandas data frame and a nice tabular data set. Like everything's just sort of nice parallel arrays. You essentially still do have parallel arrays, but now they're more ragged. And it was about a year ago that we actually switched over to a new explanation object that kind of bundled all that together and allows for parallel slicing, which just made things a lot easier to keep track of because you have data, you have feature names, you have the explanation values, you have your base values, which is like what would happen if I just give you a blank input. I have to start at some base value, and a variety of other stuff like explanation error or whatever else you might want to spit out. Those are all parallel with each other, right? They're all like a set of parallel arrays or tensors that align with each other. So this object is just a convenient way to slice them all together. So I can say, I have this explainer, I apply it to my 10 things, I get out an explanation object. I can say that explanation, bracket 0, that's going to be the first row's explanation, or colon, comma 0, it's going to be, I guess, the first word of each thing. It'd be a little odd, I guess, in text, but then you could plot it. So we have a whole plotting, subtree of the library where it's just shap.plots, all sorts of stuff. So if you're trying to plot text, there's a text plot in there. And so if you plot the explanation for sentiment, for example, as a text, you can just say explanation 0, pass that to shap.plots.text, and you will get a plot that gives sort of an interactive JavaScript overlaid heat map that has tokenized all your text according to the tokenizer that you passed and visualizes the SHAP values as computed by the partition explainer. And then you can mouse over it and see for each output which input drove it. Now, in this case, there's only maybe one output, which is a positive or negative, but it could be there's like three outputs, right? Positive, negative, neutral. That's pretty common. And then the same thing happens when you're doing, let's say you're doing translation instead of something like that. Well, it turns out that it's a bit more tricky under the hood, but in theory, for the user, it should be the same, right? You just pass the exact same thing in. And now when you plot your explanation, it's now an explanation of a whole bunch of outputs where each output is the output token, right? Coming out of this translation model. And so then you can just mouse over, click on any of those outputs, and you can see, okay, for this word in the output, this is the input effect that it had.
And so digging deeper into some of the typical workflows that people have built around SHAP and some of the potential ways that it can be applied, you mentioned that because it's just another model that you're computing to be able to determine the explanation for the model that you are trying to understand, you might be able to potentially feed that into another downstream system and be able to potentially create a feedback loop. And I'm wondering, what are some of the sort of interesting workflows that you've seen people build where they are trying to automate some of the feedback from this explanation to say that, no, this is not what I'm actually trying to achieve as an output based on these features. I actually want something different, and maybe do sort of like a meta training aspect of using these two models to play, maybe as like a GAN style approach.
On the tabular side of things, I've seen people use these downstream things for fairness computations. And I've written about it too, but I've seen people do it even before I talked about it, where they essentially take these values and then compute fairness metrics on them individually in order to essentially run all the downstream analysis that you might be interested in because essentially, what is the units of an explanation? That's important to keep in mind. The units of the explanations in SHAP are the same as the units of your output in your model. Right? So if the output of your model is in bits or log odds or whatever probabilities, that's the same units of your explanation. So that means normally that whatever analysis you're doing to the output, if it's not like a binary kind of thing, can be applied to the input per feature. That could be helpful. So that's one automated, way of doing it, to automatically create summary statistics that you wouldn't maybe expect, or apply it to the loss of the model or something like that. For the explanations, like actually trying to guide the model itself in sort of a GAN style. So the earliest work I've seen, it's roughly close to this, is like there's some work called Right for the Right Reasons, or a paper like that a while back, where basically talking about constraining why a model is doing something and not just what it's doing. We tried to extend on that a bit, and this is like a Nature MI paper, I think, recently, on how to do that for deep learning models. The real trick is the differentiability. So if you don't have gradients, it's really hard to do the end-to-end sort of loop training. Like that's the key aspect of GANs is, you're able to get a differentiable end-to-end system out of the whole thing. That restricts the type of explanation that you're able to do. And so we use sort of an expected gradients, which is sort of an expected version of the integrated gradients explanation method, which I won't get into all the depth of, but basically it relies on an infinite game extension of Shapley values, but it boils down to relying on the gradients of your model. Unfortunately, in my experience, it doesn't work as well for really deep neural nets. So I think it's a great solution for sort of shallow approaches. And we did show that it can be useful for regularizing anything you like. It's a really cool concept, right? If you think about it, right? Just like your parameters, you might want to regularize parameters, but maybe the parameters aren't really in the right form. Like maybe it might be challenging to write down an L1 regularization of the parameters of a model where if you squish one parameter, it just pops up somewhere else, right? Like, if there's 100 outputs, what do I really want small where, but if I just say, I want the feature attribution to be small, then the implementation is sort of abstracted away, right? I can say like, it doesn't matter. Or what does it mean to be smooth? Because I can always like upsample in the next layer, right? Like I could make it smooth in the first layer and then just have a times 100 in the next layer and I would get a great, but all that goes away if I regularize explanations. So we've done some of that. I think that it's challenging primarily because you have to rely on differentiable explanations. And I think those come with a lot of dangers. But they're certainly valuable and worth looking at, particularly in domains where you're willing to spend a good bit of time. One thing I will note, though, is so there's been some work on like how to trick explanations, right? How do you intentionally deceive explanations, if you will, adversarial explanation attacks. Almost always those depend on providing fake data in very special ways, such that whenever you're explaining the model, doing your perturbations, I tell you one thing. But whenever I give you real data, I tell you another thing, right? That depends on there being strong dependencies in the data structure that you're explaining. And if there are, then you can obviously just sort of have a little switch that says, pretend I'm such and such when you're perturbing me and do something else when real data hits me. If I can ever tell the difference, I can do that. But like, that's something that a person engineered it to do. But as soon as you start putting explanations in the loop, you're incentivizing your model to lie, right? Like if you ask the model, like, what can models lie, right? Thought about writing something up on this, but I haven't got around to it. So like, can models lie? Like models don't have like the emotions that would connotate the typical incentives that people would have to lie. But models are very good at following incentives. And what would the incentive to lie be? It would be to tell me one thing while achieving another goal, right? So essentially, if you put the constraint of an explanation on a model and you say, make my explanation look like this, but have high accuracy on this potentially sensitive task. Well, what's the best way to do it if, like there's a reason you're putting this constraint here. It's because apparently it's not in perfect match with the task you have. And so you're essentially incentivizing your model to lie to you, right? Please tell me this while doing this. Like that's essentially what you're saying to your model. So I'd be very cautious, as fun as it sounds, to set up a GAM like that. You have to realize that you are incentivizing deceptive behavior.
It's definitely a very interesting insight and something that I hadn't really thought of, but that is pretty hilarious to consider. Just like this completely sort of emotionally agnostic system being incentivized to tell you what you want to hear, regardless of its applications to reality.
Yeah. So it's definitely one of those things where, you want to be careful.
Yes.
Please tell me what I want to hear. Well, okay, but remember, it will.
Right. And so in terms of the ideas and assumptions that you had as you first began exploring this overall area of explainability and building the SHAP project, I'm wondering what were some of the assumptions that you had that have been challenged or updated as you have dug deeper into the problem domain and as more people have started using SHAP in their own work?
Well, I would say that the breadth of use was a bit surprising at first. Like I didn't really expect how many ways that it would be useful, which has been fun and scary in certain times. Like you want to make sure that it's used in the right ways, not the wrong ones. So I guess that was a assumption. I don't know if it was spoken or not, but it was a surprise. I would also say that there's like a lot to maintaining a repo that you don't imagine when you start off. So I've probably not done the best on staying on top of everything, but at certain points there's an investment in maintenance that is a zero-sum game with an investment in future research as well. And so that's been a blessing and a challenge, I would say, to figure out how best to both be helpful and be effective at the same time. So that's been good. I also learned a lot about what it was like to depend on other modules, just how does it live in the Python ecosystem. And, I think I mentioned I started off in Julia, then I went to Python, and then I was like, well, I got to run some of these things faster. So then I wrote a C module, and then I found Numba worked out pretty well. And so I used that. And then NVIDIA was kind enough last year to contribute some CUDA code for the tree explainer. So you can use GPU explanation acceleration. And so that's kind of opened my eyes to all the ways that compilation can fail in all these systems in Python. And I underestimated, I think, how much that takes. I also underestimated what it was like to depend on large libraries like TensorFlow or PyTorch. So I remember I have a deep explainer that like reached inside and traversed the graph of a TensorFlow or PyTorch graph. But TensorFlow 1 to 2, suddenly it moved everything from Python to C. Everything just disappeared. It's like, so just an understanding of what is the maintenance debt that you take on when you put something out. It's a real learning experience.
For people who are interested in being able to apply the capabilities of SHAP to the work that they're doing, I guess how much overall domain knowledge and understanding of the principles of explainability is necessary, and what are some of the challenges that they face in being able to use SHAP most effectively and interpret and understand the outputs that it is generating and how that may be best used to feed back into the next iteration of their sort of exploratory development cycles?
I think it's hard to know from the outside. Like I've even seen studies on this and it's hard to, like sometimes people are like, oh, well, this is easier than this, but it's really like some subtle detail that was really the whole issue. And so then you're like, well, what have I really learned? I've just learned that, this particular aspect, but then I could change that, but then I don't know, so I wouldn't want to promise if you know this, you're safe, or to say like you should never use it if you don't understand this book of knowledge. But I would say that it's important to know, first of all, what your features mean. If you don't know what your features mean, SHAP is not going to be very helpful. It's not going to be effective because it will tell you something's going on with feature 5. And you're like, great, okay, PCA 5 means something, I guess. I don't know. And so that's the clear kind of limitation, is if you don't have any domain or very little domain knowledge of your features, then what your model is doing won't mean anything to you. So most people who are developing models have at least some understanding of what their features are doing, even if they aren't, quote, the domain expert. Like, they can still look at it and be like, oh, it's the loan rate that's doing. I don't know what loan rate is, but so there's definitely some digging that will need to happen. But at least, I think it's fair to use it, find out what the important ones are, and then learn about those. Right? You don't have to read all 100 first. I would also say that it is important to know what the alternative is. So whenever you're doing an explanation, people implicitly in their head work with alternatives all the time, right? Like when you go to work and you say, I was late, and you say, it's because I hit a red light. Everyone assumes the alternative is a green light. Right? They don't assume the alternative was that I didn't get airlifted. The cops didn't come and ride me in a caravan. There's lots of alternatives on how you could have gotten to work, but people always have a typical alternative in their head. And you may have one in your head, and it's important to make sure that that's roughly what the model has and what the explainer has actually implemented. Because if they're wildly different, you could lead yourself astray. And that's essentially understanding the masker. So if you're writing a tree model, by default, it can actually pull out the background training set from the leaf counts. And so you're essentially comparing it to the average. So that's a typical thing. But if you forget that you're comparing to the average, then it can get you lost. Or if you're doing some really tricky model like text or images, you need to know what is actually happening in the perturbations. Am I blurring chunks of the image? That's important to know. I guess the two last things I would say is, one, you need to know the output of your model. Just like you have to know the inputs of your model, if you don't know what the outputs are, then you're in trouble. And know what they mean is fuzzy, right? Because a lot of people work with log odds, even though they don't really know what log odds are. They're just sort of the thing that came before the probability before they got squished. And so there's a lot of subtleties that can get washed over, and sometimes that's fine. But you just have to understand that your understanding is limited by your understanding of the output units that you're working with. And of course, you should always consider the explanation error. In other words, if you're plotting a scatter plot and there's tons of vertical variability, that means there's tons of interactions, and you should just keep that in mind. One other thing I think that would be helpful when people are thinking of context, oftentimes when people train a model, they want to know how the world works. But that's not what you learn. What you learn is how your model is working when you're explaining it, not necessarily how the world's working. So if I am someone doing sales and marketing, and I want to know my ad spending, and how much is it worth to spend my ad spending? I could train a model that predicts here's how much I spent on ads, here's how much money I make. The model says X. But SHAP isn't a replacement for causal inference. It's very useful to explain heterogeneous treatment effects inside causal inference packages, but it does not magically turn a observational model into a causal model just because you know what it's doing. And so that's important to keep in mind. There is a close connection between at least SHAP and most other explanation packages and causality, where you actually are doing causal inference, but you're doing it on the model, not on the world, right? I am actually running a randomized controlled trial, but it's on my model's inputs. It's not on the actual world. So, that's kind of an important distinction to keep in mind that people I have seen kind of go a bit astray on.
In terms of the sort of alternatives, you mentioned, there might be other libraries people are using to determine the sort of explanations of their model outputs. And I'm wondering if you can just kind of briefly give a sort of landscape, sort of 30,000 foot view of some of the different projects or approaches that people might use for explainability, in lieu of or in addition to SHAP.
So kind of categorize the field, I suppose. There's the model agnostic section of things. So there's, Lime, SHAP, those are model agnostic approaches. And they don't necessarily have to make assumptions about your input, output, or model type. Okay? And I would say that there's then some game theoretic approaches, there's the local linear approaches, and then there's what I would call sort of, I don't know if classical or heuristic is the right word. I'm not sure what to use. Partial dependence plots, for example, fall under this, or, standard global feature importance measures where you just, permute a column in your data. Many of those correspond to different choices that people make. And if you're thinking about feature attribution, I was actually worked with a grad student at UW. He did a nice overview of feature attribution and all the different choices, and had 30 different methods in there, and made a big table of if you make these choices, you get these methods, you make these choices, you get these methods. So if people who want to go details, I recommend that. And then there's also on the structure side of things, there's the implementation from a variety of startups and also larger companies who have sort of an ML lifecycle in view. And so they're interested in sort of engaging folks in a way that helps them understand an ML lifecycle. And some of those are very verticals focused, right? So they could be like, I am going to build an expert's, very well tailored system for financial services products that have output explanations of a certain particular type that will work well for this domain. And I'd say that normally that comes with a significant benefit of people who know what they're doing in that domain. Of course, there's always lock-in whenever you're considering non-open source stuff, but I think there's a lot of good people doing great work there. So, I thought about going that route at one point, building stuff and commercially supporting it. There's also, I say, a very large emphasis on building interpretable models. And I think that should always be where people look as well. So there's really great work. Rich Caruana is a coworker of mine who works on generalized additive models a lot, and InterpretML is a package a bit involved in there with SHAP's integrated in there for some external models, but the core interpretable model offering there is sort of a direction to have zero explanation error boosting machines essentially. And I think those are excellent directions that people should consider. And I think what else? There's a lot of, I think, model specific, maybe a good way to say it is there's a lot of perturbation methods. So Marco is another coworker of mine he did Lime. He's also done one called Polyjuice, which is kind of interesting, and other counterfactual based explanations. And they are based on essentially perturbing text and showing you potentially surprising, semantically equivalent changes that change the output of the model. So SHAP is all about summarizing lots of counterfactual perturbations, but it could be that you actually just want to see specific ones, right? That's also a helpful thing. So feature attribution is about a summary of many counterfactuals, but there are lots of packages out there, particularly in the NLP space, which I think are good at finding really interesting counterfactuals. And then they just show you one of them. It's very concrete. It doesn't give you as big a picture maybe, but it gives you very concrete information about a specific behavior. Same thing for images. There's some fun stuff on finding the closest image that will change the class while remaining visually sane. I'm not adding noise to the model. We're adding smooth, large scale changes to the image. And then you can see some really interesting sort of adversarial explanations, if you will. That's really fun. There's stuff like Beam Kim a while back did some stuff on concept vectors and sort of latent vector representational spaces. So that's a really helpful concept, which isn't necessarily orthogonal to SHAP or any of these other explanation methods, but it's a way to come up with concepts from things that would otherwise be distributed. So we talked earlier about pixels maybe not being the right language. This could be really helpful. Or I think there was the work on bottleneck models, where you essentially, it's kind of an interpretable model again, where you're trying to create features that make sense from your data by either anchoring them to some external labeling or something like that.
And so in terms of your own work and your own usage of SHAP, I'm wondering what are some of the applications that you have found useful in the research that you're doing, if you're able to speak to that?
Yeah, it changes over time. I would say at this point, and probably for the last few years, I don't really ever build a model without applying SHAP to it at this point, because it's just been, it's a big part of how I understand what the model is doing and how it's worked. So I would say when I was doing a lot of sort of medical stuff, whenever we were working with collaborators, be building models, and I would be trying to explain those models, and then that would inform downstream experiments or follow-ups as they're essentially trying to understand the signal in the data. So recently I've been working more on NLP models, finding errors in them and using them against each other and all sorts of fun things. And so in that case, whenever we're looking at a overt mistake by one of these NLP systems, I found it useful to just throw that into SHAP and make sure that the part of the sentence that I think perturbing, that's really driving this, right? Is actually driving it. That's helpful. I've also used it to substructure data sets. So found it helpful to run SHAP, compute, the driving effect on either the loss and then sort of look into that per feature, or on the model output and then just cluster by that. So then I find a chunk of data that has the same output for the same reason, and that's usually interesting.
In your experience of using SHAP for your own work and in working with the community of people who have started using it for their own applications of machine learning models and understanding the sort of motivations that go into the outputs, what are some of the most interesting or innovative or unexpected ways that you've seen it used?
Well, let's see. There's always the applications that are surprising. When people say, "Hey, here's my paper on deep sea life diversity, and here's how SHAP quantifies, the fish populations of the Pacific or something. Well, that's really cool. And I would have never imagined that was not what I had in mind when putting this together. So that's kind of fun. Or like, I've seen, I think I mentioned earlier, seen fun applications where people are using it to kind of manage the boundary between automated and human decision making, where they have a whole system that could make the decision, but people make the decisions too. And so how do you inform the people with what the computer would have been doing? I've seen the sales example, where salesmen are informed by it. I thought that was kind of fun. I've seen like MBA teams use it for like modeling their statistical modeling, like how can we improve whatever. I think maybe one of the most creative uses was one where they built it a whole like data cleaning and anomaly detection system based on the feature attributions. That's pretty cool. People using it for, the fairness, I thought was kind of interesting to look at because you get a much more rich understanding of like a lot of the fairness rules here in the US at least are based on just a straight up disparity. Like that's the first watch case. Like if the output of your model is starkly different between two protected classes, then questions start being asked. And so I thought it was interesting to see I saw a variety of startups do stuff where they would segment by feature. So that you could be like, well, feature 5 is actually what we should be asking questions about. I thought that was kind of fun.
In your experience of building the SHAP project and using it to explore the overall space of explainability and machine learning and AI, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I've learned that theory is nice, but practice is a necessity, if that makes sense. So getting both is kind of hard sometimes. Sometimes that things have seemed like they would be, maybe I'm just too optimistic, I guess, but like this is going to work great. And then it doesn't. So it's been really good to have a good feedback loop, I think, that I've really valued. You already mentioned the, managing code debt good ways. It's a learning experience. I think I learned a lot about like speed and how to do it correctly, how to trade off performance and not when you're writing a Python package, I'll write this whole thing in C++ and like put a little binder or write the whole thing and not care about speed and just seeing the different applications because sometimes it just doesn't matter and sometimes it does. So that was definitely a learning experience. I've also been pleasantly surprised about, it's great to work on open source code. Like it's a helpful community, like people love to contribute stuff. And as bad as I am at, being a full-time maintainer, I think that it's been, from my perception, a good thing for a lot of folks. And I appreciated that.
And for people who are interested in being able to gain more visibility into the motivations for the decisions that their models are making, what are the cases where SHAP is the wrong choice and they might be better suited with choosing a different model architecture or using one of the other sort of libraries or approaches that you mentioned earlier?
I would say that, well, going back to that example of that hackathon where there was 2 different goals, right? There was a reason, at least as I saw it, I thought there's a value for sort of the information content of a feature. How informative is this on my prediction? There's also the gradient. What's the closest action to increase my score? Those are different goals. The first one, I say, SHAP is as good as many others for that application, probably better than mine at least was. And for the other one, SHAP would be just not the right answer, just not the question it's answering. So that would be the wrong explanation method if your goal is to find the nearest counterfactual that will lead to something. So I would say there are other methods like Amit Sharma has some DICE method, I think, that's here at Microsoft. Marco's done one on anchors, I believe. These are all counterfactual based things. Like if I change so much, what would need to change or not change in order for value to stay the same? So if you're looking for specific counterfactuals, then it's not the purpose of feature attribution. So I think you should look somewhere else. I think I also mentioned this before, but it's the wrong tool if it causes you to fail to use another tool, even if they could be used well together, if that makes sense. So if SHAP makes you think if you don't need to think about causal inference when you're really do, then that would be a mistake. Not because it's not useful for your problem, but because it doesn't solve that question. That would be another case. And I think I don't know if it's the wrong tool question, but like you could certainly use it wrongly if you don't consider the explanation error and the impact that could have on your system, your debugging choices, or downstream applications. So one of the upsides of having sort of inherently interpretable or a simple model is that you're forced to have zero explanation error under some definition of that model being the explanation. But you're very fixed to that model. With a tool like SHAP, you are now free to stick anything you like in there. And if you were to not care at all about the complexity of those models and hence the explanation error of the, what you're interpreting, You could hide a lot in there if you aren't careful. I think there's a lot of value in giving that flexibility, but you have to recognize it is flexibility, and there is some cost to going up into complexity. There's also some cost, I should note, in going too simple, right? So we demonstrated sometimes in our papers, if you do use a linear model when your data is not linear, that linear model will then begin to depend on weird cancellation effects between your features in order to become slightly nonlinear, because those features are slightly nonlinearly related. And so it can do some sort of weird stuff. And suddenly your model is interpretable because, it's only got 10 coefficients. Those coefficients, you have no idea what they really mean, because they're, cancellation of 3 nonlinear effects with the fourth one. And you didn't even know that they were nonlinear to start with. It was just a data set. And so there is a danger to going too simple if that simplicity does not match the real world, because then it forces your model to do weird things. And then the discrepancy between the model and the world becomes so large that becomes problematic.
And as you continue to use SHAP and support the community that's grown up around it, what are some of the things that you have planned for the near to medium term? And are there any particular areas of help or contribution that you're looking for?
Yeah, so this last year here at Microsoft, we did a rotation program, and they were generous enough to have a whole team help out for a little bit on some of these NLP explanations and some image stuff too. And so we have a lot of nice code in there. One of my plans is to write up a paper to document and share that. And then also maybe write up a blog or something, just document and share that with folks. So I think there really is, a very nice way to dig into a lot of NLP models. There's a lot of other great alternatives out there too. But if you're looking for game theoretic approaches, I think this is, one of the most accessible ones out there. So I think really getting that well documented would be good. We had talked about trying to create this explanation object, which is sort of this parallel arrays, really applies to the explanations of all sorts of things. It applies when you're talking to interpret ML, people realized it applied directly to the output of their explainable models, because their explanations are actually the same form as SHAP. And so it's can we produce a common object? And so I think doing a little bit more of that would be great. I also think going forward, understanding your model is important, but so also is understanding the data that goes into the model, right? So there's a lot of structure in models, and it's great to understand that. But if you don't understand the structure in your data as well, you are flying a bit blind. So we added some stuff in SHAP where it actually, the bar plot, you can create a hierarchical clustering of tabular data at least, and it will plot that and show you what is the statistical redundancy. So what's the predictive power redundancy between two features? And I think that is really helpful, because oftentimes a model is just arbitrarily choosing one feature over another because they're redundant, or there's this whole cluster that's really got a complex interaction. So I think going forward, I'd like to incorporate that more into the explanation process, so that people are not only looking at the model, but they're looking at the model with the data structure in context. I think could be really helpful. In terms of assistance and help on things here, I feel like there are PRs are wonderful, and people have been doing a lot of those. And so if anyone's interested in doing sort of more long-term engagement where they could end up reviewing PRs and, being, the touch point for a chunk of the code, that's, I think, would be the most valuable going forward.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose a movie I watched recently called Reminiscence. That's a recent one that came out with Hugh Jackman, and it's set in the near future where global warming has caused more waters to rise, and a lot of people have decided to kind of descend into living in their memories as their sort of way of passing the time and not having to deal with the realities of the current world, and just a lot of interesting storyline that comes up around that. So definitely worth taking a look if you're looking for something to keep you entertained. So with that, I'll pass it to you, Scott. Do you have any picks this week?
I read Augustine's Confessions, and I was pleasantly just engaged with what it was like to kind of walk through intellectually with someone in a very different world and a very different time frame. So I'll pick that.
Well, thank you very much for taking the time today to join me and share the work that you're doing on SHAP and trying to help support the challenge of explainability for machine learning. It's definitely a very interesting problem area, and I appreciate all of the insight and thought that you put into it. So I appreciate you taking the time on that, and I hope you enjoy the rest of your day.
Thanks, Tobias. I appreciate it.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.